B.A Geography Semester 6 Geographic Information System Lesson 6 Raster Data Model. Objective: the raster data model is widely used method of storing geographic data. The model most commonly takes the form of grid-like structures that hold values at a regularly spaced interval over the extent of the raster. Rasters are especially well suited for storing continuous data such as temperatures and elevation values, but can hold discrete and categorical data such as land use as well. In this chapter, we get to discuss the detailed explanation about the raster data model, several methods that are used to encode the raster data, several advantages and disadvantages of raster data model. Raster data model: define the world as a regular set of cells in grid pattern. The raster data model consists of rows and columns of equally sized pixels interconnected to form a planar surface. Typically, these cells are square and evenly spaced in x and y direction. The phenomena or entities of interest are represented by attribute values associated with each cell location. These pixels are used as building blocks for creating points, line, area, network, surfaces. Although pixels may be triangles, hexagon or even octagon, square pixels represent the simplest geometric form with which to work. Raster data sets have a cell dimension defining the size of the cell. The cell dimension specifies the length and the width of the cell in a surface unit. Example: the cell dimension may be specified as a square 30 meters on each side. The cells are usually oriented parallel to the x and y direction. Thus, if we know the cell dimension and the coordinates of any one cell, example the lower left corner, we may calculate the coordinate of any other cell location. In the diagram, you can see a pixel cell is located in a rows and columns manner. So, whenever we know the x and y coordinate of that pixel, we can easily locate it in the figure. Raster data model are natural means to represent continuous spatial features or phenomena. Elevation, precipitation, slope and pollutant concentration are examples of continuous spatial variables. These variables characteristically show significant changes in value over broad areas. The gradients can be quite steep, for example at cliffs, gentle, example long and slopy ridges, or quite variable, example rolling hills. Because raster data may be dense sampling of points in two dimensions, they easily represent all variations in the changing surface. Raster data models depict these gradients by changes in the value associated with each cell, usually defined at a point in the center of the cell. The coordinate applies to the entire area covered by the cell. Positional accuracy is typically expected to be no better than approximately 1/2 of the cell size. No matter the true location of a feature, coordinates are truncated or rounded up to the nearest cell center coordinate. Thus, the cell size should be no more than twice the desired accuracy and precision for the data layer represented in the raster, and should be smaller. Each raster cell represents a given area on the ground and is assigned a value that may be considered to apply for the cell. In some instances, the variable may be uniform over the raster cell, and hence the value is correct over the cell. However, under most conditions, they are within the cell variation, and the raster cell value represents average, central or most common value found in the cell, while raster cell often represents the average of or the value measured at the center of the cell. They may also represent the medium, maximum or other statistic for a cell area. A raster data model may also be used to represent discrete data. For example, to represent land cover in an area, raster cell typically hold numeric or single letter alphabetic characters. So, some coding schemes must be defined to identify each discrete value. Each code may be found at many raster cells. The diagram shows how the image in the real world is being converted into raster data format. See, you can observe how the road is being pixel dated, then we have houses is being pixel dated, then the water body is being pixel dated, then the forest also we have been showing the area of the pixel is being marked. So, thus we are converting the real world features into raster data format. Raster cell values may be assigned and interpreted in at least 7 different ways. A raster cell as a point physical value, elevation as a statistical value and as a discrete data. Land cover also may be interpreted as a class code. The value for any cell may have a given land cover value and the cells may be discontinuous. Example, we may have several farm fields scattered about our area with an identical land cover code. The discrete codes may also be used to identify a specific, usually continuous entity. For example, a county, a state or country. Raster values may also be used to represent points and lines as IDs of lines and points that occur closest to the cell center. The raster cell assignment may be complicated when representing what we typically think of as discrete boundaries. For example, when the raster value is interpreted as a class code or as a continuous region ID because of the reliance on a uniform series of square pixels, the raster data model is referred to as grid based system. Typically, a single data value which will be assigned to each grid locally. Each cell in the raster carries a single value which represents the characteristics of the spatial phenomena at a location denoted by rows and columns. The data type for that cell value can be either integrated or a floating point. Alternatively, the raster graphic can refer a database management system within open-ended attribute tables can be used to associate multiple data values to each pixel. The advance of computer technology has made this second methodology increasingly feasible as large data sets are no longer constrained by computer storage issue as they were previously. The raster model will average all values within a given pixel to yield a single value. Therefore, the more areas covered per pixel, the less accurate the associated data value. The area covered by each pixel determines the spatial resolution of the raster model from which it is being derived. For example, whenever you are seeing an image and you try to zoom in, so all you can observe is all the pixels that are being present in the area. So as we zoom in, the resolution is being decreased. So the resolution, the spatial resolution is very much important for creating the pixel value. Specifically, resolution is determined by measuring one side of the square pixel. A raster model with pixels representing 10 meters by 10 meters or 100 square meters in the real world would be said to have spatial resolution of 10 meters. A raster model with pixels measuring 1 kilometer by 1 kilometer, 1 square kilometer in the real world would be said to have spatial resolution of 1 kilometer and so forth. Care must be taken when determining the resolution of a raster because using an overlay coarse pixel resolution will cause the loss of information, whereas using overlay fine pixel resolution will result in significantly increase in file size and computer processing requirements during display or analysis. An effective pixel resolution will take both map scale and minimum mapping unit of other GIS data into consideration. In the case of raster graphics, with coarse spatial resolution, the data value associated with specific location are not necessarily explicit in the raster data model. For example, if the location of a telephone poles are mapped on a coarse raster graph, it would be clear that the entire cell would not be filled by the pole. Rather, the pole would be assumed to be located somewhere within that cell, typically at the center. The figure shows the land use and the land cover image. Several methods exist for encoding raster data from scratch. 3 of these models are as follows. Cell by cell raster encoding. This minimal intensive method encodes a raster by creating records for each cell value by rows and columns. This method could be thought as large widespread sheet wherein each cell of a spreadsheet represents a pixel in the raster image. This method is also referred to as exhaustive enumeration. Run length raster encoding. This method encodes cell value in run of similar valued pixels and can result in a highly compressed image file. The run length encoding method is useful in situations where large group of neighboring pixels have similar value. Example, discrete data set such as land use, land cover or habitat suitability, and is less useful where neighboring pixel values vary widely. For example, continuous data sets such as elevation or sea surface temperatures. Quadtree raster encoding. This method divides a raster into hierarchy of quadrants that are subdivided based on similar value pixels. The division of raster stops when the quadrant is made entirely from the cell of the same value. A quadrant that cannot be subdivided is called a leaf node. The figure shows how the data is being channelized by cell method. This figure shows the run length method of using or classifying the map details. Here the data is being converted into quadtree raster model. Storage and file formats. Raster records one or more values at each grid point. Grid values may vary, simply recorded row by row, starting at the upper left corner in the same manner that the text is written in English. Alternative ordering system may be used to improve efficiency, including row prime, Morton or Pino-Hilbert methods. Memory demands for raster are influenced by the type of data recorded. Example, Boolean, integer, float or string. The resolution and the spatial extent of the raster and any comprehension applied to the image. Compression can be used to exploit repetition or redundancy in the data to reduce overall storage demands, and many schemes are available accomplish this, including chain codes, block codes, run length codes and quadries. Rasters may be stored in any number of formats or containers. They are typically stored in a binary format for the sake of efficiency, but plain text formats are not uncommon. With ISRI's ArcInfo ASCII grid perhaps the most widely used of this type. Binary raster formats are too numerous to exhaustively list, and the reader may wish to consult the Geospatial Data Abstract Library project for a list of its 154 readable formats. Many formats originally designed for photographic images have been used as raster containers, including JPG, JPEG, 2000, PNG and TIFF. These have the advantages of easily moving raster data into and out of non-GIS data processing system. Nearly all containers feature a mechanism for compression of data to reduce file sizes, but vary in the degree to which they allow to lossless compression in some cases. Some reduction of data fidelity may not greatly diminish the value of the data set. For example, digital orthophotos have been widely distributed in the JPEG container, even though some often imperceptible data loss will occur in the process of encoding the data for storage. In other cases, example, digital elevation models, perfect data fidelity is deemed more critical, and so these are often distributed in formats that feature lossless compressions. Example, GeoTIFFs. Formats often differ in the type of data that they can hold. For example, instances, PNGs can hold any integer based data with a maximum of 4 bands, while TIFFs can hold float data and a large number of bands. The recent big TIFF format extends the capabilities of the following of the TIFF format, allowing for much larger greater than 4 gigabyte file sizes. Image based containers have also proven popular because they interoperate more easily with non-GIS software. Proprietary storage formats, example EMRC, often features high compression rates, but concerns with documentation, longevity and interoperability have prompted the development of a number or efficient open non-proprietary alternatives, example JPG 2000. Georeferencing information for raster images is embedded either directly in the header of the container file or via ancillary files that are distributed with the raster. A world file is a common example of the later approach, where a separate plain text file describes the position in the geographic space of the center of the upper left pixel as well as x and y resolution of the raster. Advantages and disadvantages of raster model. The use of a raster data model confers many advantages. First, the technology required to create raster graphics is inexpensive and ubiquitous. Nearly everyone currently owns some sort of raster image generator, namely a digital camera. A few cellular phones are sold today that don't include such functionality. Similarly, a plethora of satellites are constantly beaming up to the minute raster graphics to scientific facilities across the globe. These graphics are often posted online for private and or public use, occasionally at no cost to the user. Additional advantages of raster graphics are the relative simplicity of the underlying data structure. Each grid location represented in the raster image correlates to a single value or series of values if attribute tables are included. This simple data structure may also help explain why it is relatively easy to perform overlay analysis on raster data. For more on overlay analysis, this simplicity also lends itself to easy interpretation and maintenance of the graphics relative to its vector counterpart. Despite the advantages, there are also several disadvantages to using the raster data model. The first disadvantage is that the raster files are typically very large, particularly in the case of raster image built from cell by cell encoding methodology. The sheer number of values stored in a given data result in potentially enormous files. Any raster file that covers a large area and has somewhat finely resolved pixels will quickly reach hundreds of megabytes in size or more. These large files are only getting larger as the quantity and quality of the raster data sets continues to keep pace with quantity and quality of computer resources and raster data collector, example digital cameras, satellites. Second disadvantage of the raster model is that the output image are less pretty than their vector counterpart. This is particularly noticeable when the raster images are enlarged or zoomed. Depending on how far one zooms into a raster image, the details and coherence of that image will quickly be lost amid a pixelated sea of seemingly random colored grid cells. The geometric transformation that arise during map reprojections efforts can cause problems for raster graphics and represent a third disadvantage to using the raster data model. As described in changing map projection will alter the size and the shape of the original input layer and frequently result in the loss or addition of pixel. Display of pixel loss and replication in reprojecting raster data from the sinusoidal projection. These alterations will result in the perfect square pixels of the input layer taking on some alternate rhombical dimensions. However, the problem is larger than a simple deformation of the square pixel. Indeed, the reprojection of a raster image dataset from one projection to other projection brings changes to pixel values that may in turn significantly alter the output information. Modeling the accuracy of image data reprojection. The final disadvantage of using the raster data model is that it is not suitable for some types of spatial analysis. For example, difficulties arise when attempting to overlay and analyze multiple raster graphics produced at different scales and pixel resolution. Combining information from a raster image with 10 meter spatial resolution with a raster image with 1 kilometer spatial resolution will most likely produce a nonsensical output information, as the scales of analysis are far too disparate to result in a meaningful and interpretable conclusion. In addition, some network and spatial analysis, example determining directionality or geocoding, can be problematic to perform on raster data. Summary: the raster data model is widely used to encode GIS data. Examples include digital elevated models (DEMS) such as the ETOPO-1 Global Relief Model, elevation derived visualization and products Kenley 2017. Remotely sensed data includes aerial and radar imagery. Methodological variables such as temperature and rainfall interpolated from point sources. Categorical rasters such as the National Land Cover Database. The gridded population of a world data set which grids values originally recorded via administrative units. Digital scans of historical maps. Exported cartographic products such as digital raster graphic topographic maps.